Hi, everybody. So today is Wednesday, September 13th. And if we refer to our Moodle page here in statics, we learn that it is a big day because we have chapter 2 homework is due. So many files. And I extended that. It was originally due Monday, but I realized that was not practical. So I extended the deadline till midnight tonight. And we also have the quiz over chapters 1 and 2, which is due by midnight tonight. Now, I just want to say, if anybody needs a little extra time, just let me know and we will take care of that. But I have a question on chapter 2. And what is your question? What number is the problem? 2.106. All right, let's find the chapter. Is it this one probably? I'm gonna find out 2.106. Oh, there we go. Solve problem 2.105. Knowing that alpha is 45 degrees, correct? All right. Do you have a specific question or would you like me to just work through? It's a deal. Okay, fine. That's good. So basically 2.105, I'll read through that and then I will alter it so that alpha is 45 degrees. We have a 12-pound circular plate, 7 inches in radius, supported as shown by 3 wires, each of which is 25 inches long. Determine the tension in each wire, knowing that alpha in this case is 45 degrees. Okay, so basically we have our geometry is that we have 3 cables. So I'm just cutting to like a free body diagram here. Let me think about how I'm going to do this. I'm going to draw it based on this and then I'll show you the screen because sharing the screen, I mean, you can see what I'm drawing up in the little corner, but I'll make it big in just a few minutes. We know that each one of those is in tension, meaning that if we take it from the point of view of the plate down here, that they're going this way, okay? And then we are further told that the radius of this plate is 7 inches and that the length of each cable is 25 inches. All right, so these cables are each 25 inches in length and their distance from the center, which is where I assume this point is, point A and point O, I assume that they're directly, that A is directly above O, 25 inches, 25 inches, 25 inches, and A is A to D to O. A to D is on, if we drew our coordinate system, X, Y, and Z, this is going to be on the X axis. And then these two are each, this is going to be like impossible to draw the way I have it, so I'm going to do like this. And we have a 45-degree angle on each of these from the Z-axis. Okay. And we are told that the plate has a weight of 25 pounds, which means that we can think of that as a 25-pound force acting directly through point O, assuming that the plate is homogeneously, the weight is distributed homogeneously on the plate, and that it's that O is directly in the center and the weight is 25 pounds acting downward, which would be the Y direction. All right. It says 12 pounds. These are 25 inches and this is 12 pounds. That will work better. All right. So the first thing that we need to do is to set up the directional vectors on each one of those tensions. And then so this is D, C, and B. All right. And I'm probably going to have to keep drawing this over and over again because that's what happens when you don't have good when you don't have a good drawing to begin with. So, all right. So basically, this is what we know. We know that in order for this to sit still, that the summation of forces in the x direction have to equal 0. The summation forces in the y direction have to equal 0. And the summation forces in the z direction also have to equal 0. So to begin working this problem, we know that if we take the force A to D, the force in AD, that's going to equal, this would be a vector, lambda AD times the magnitude of the force in AD. All right. And similarly, the force in AC as a vector is going to be lambda AC times the magnitude of the force. And last but not least, AC, DA, and I've got my letters kind of mixed up, but let's go DA. Let's go AC, AD, AB. There we go. Let's leave it like that. This is going to be lambda AB times the force in AB. All right. So the deal is the force in these three forces are the tensions in each of those cables. And we know that they're pulling up because it's suspending the plate. And so we know that we have our arrows drawn correctly in this diagram. So the trick becomes getting lambda, or the unit vector, along each of those dimensions. So for AD, not the force in AD, but the dimensions, the geometrical force, we know that AD is 25 inches long, and we know that it's directly on the x-axis. So in other words, AD has some component in the I direction, which is a negative, and some component in the Y direction, which is positive, but no component in the K direction, because it's directed right along that axis from the original picture. So let me just take a peek here. So we can see A to D is just straight over that axis, is what they're implying. Okay, so what does that mean? Well, there's a couple of different ways that we can do this, but we can, for example, just take this geometrical triangle here, which we're told that the radius, oops, you can't see that picture. The radius is 7 inches directed in the x direction. So we could find this angle, right? And we know that the hypotenuse is 25. And so if we're looking for the component of AD in the I direction, it's going to be the piece that's directed along this axis. So if we found this as being theta, we could say we have the adjacent and the hypotenuse, which is cosine. So we can punch in that number. I'm going to do this a couple different ways, just however you're more comfortable with the trig. That's 7 divided by 25. And that number is 73.7 degrees. So this theta is 73.7 degrees. All right, that means that in the I direction, it's going to be the hypotenuse, 25, times the cosine of 73.7 degrees. In the J direction, it's going to be 25 times the sine of 73.7 degrees. And in the K direction, it's equal to 0. All right. So I'll do, let's see. So we have 70 cosine, 73.7. Multiply that number by 25. We get the x component is 7.017 I, and it's negative, plus 25 times the sine of 73.7 So that's 23.99 or roughly 24J plus 0K. All right, then how do I find lambda? Lambda AD is equal to these numbers divided by the 25 because that's the length of the whole thing. So AD is equal to lambda AD is negative 7.017 divided by 25I plus 24 over 25J plus 0K, right? And divided by 25, this number, because I just had it, my calculator is 0.96J. And so this number is negative 0.28. Okay. Now, what I'd like to point out here is just a simplification step. This is the cosine of that angle, right? Now, you don't have to know that, but it can make your life a little bit simpler, can save one step. These are all the cosines of the angle that it makes an angle that particular side of the vector makes an angle with. So in other words, that was the most awkwardly worded sentence, but this cosine of this angle would be lambda in the J direction. Okay, so, but it's kind of went through this a long way, but it's kind of like the old reliable way that will work every single time. Okay, so we have piece number one. Now we need to find lambda in the other two directions. And we have lambda. First of all, we have to find the vector AC. And the interesting, AC is a little bit more complicated. It's not terribly complicated, but it's a little bit more complicated because it has, it's in all directions, right? So in other words, we have an I, J, and K component. So it's going to be something I, which I have to go back to the textbook because I've drawn such a wretched picture here. I can't really tell what it looks like. Okay, so C to A in the I direction is positive, isn't it? So C to A in the I direction is positive. In the J direction, it is also positive. And in the K direction, it's coming out of the page, so it is also positive. Let's go ahead and set up our signs for AB before we finish the rest of that work. If we look from A to B, it's going to the left in the X direction, so it's negative. J is still positive. And this time K from here to here is going back into the page, so that is also negative. All right, so now we need to determine the lengths, and A and C and AB are going to look similar in the XZ plane, which is the plane of the plate. Okay, so let me just draw the plate itself. And I will put this big on the screen in just a minute. And here's point 0. And what we find is this line from A to B is the radius, so it's 7 inches. This angle's 45. This angle from A to C is also 45 degrees, and the length is 7 inches. Okay, so this is the XZ plane. Now, A and B, let me think of how to describe this. So we need to find this measurement, which we know that that's 7 in each case, and we know that it's 25 inches tall. So in other words, it's a triangle. If we put the triangle right here, that would be, how am I going to draw that? 7 inches, 25, I'm sorry, not 25 tall. It's going to be 25 like this, okay? And we know then what this angle is because we already found it for our previous situation with AD. So that angle is 73.7 degrees right here. But now it's not going to drop it onto the, it's not going to drop that onto the x-axis or the z-axis. It's going to give us this piece and this piece, okay? So what that means for us is that we need to take this value and we need to swing it over 45 degrees. And we do the same thing on the other cable as well, just that the signs are different, all right? So in other words, in this case, we have components where we have part of that value, which is, we came up with some number here, I can't remember, 7.017 or something like that. 25 times the cosine, yeah, which is actually just 7, right? And we swing that up. So this is 7. So how much of it comes down like that is actually going to be times the cosine of 45 degrees. Okay. And the same here. This 7 will swing up here, cosine of 45 degrees. Then that will be on the x measurement. On the z measurement, it's going to be 7 times the sine of 45 degrees. Well, what do we know about the sine of 45 degrees and the cosine of 45 degrees? The sine of 45 is 0.707. Cosine of 45 degrees is also 0.707. So good news is they're equal. So what we have then is a triangle that looks like this. This would be the x component, and this would be the z component, and this would be 7 inches. All right, so if this is 45, x is equal to 7 times the cosine of 45 degrees. Z is equal to 7 times the sine of 45 degrees. And let's see, times 7. That means that they're both 4.95 inches. Okay, so if we go back to this drawing, we can also see that AC and AB also have those, they both have the same dimensions. They're both 4.95 along that particular axis. But the answer is that the signs are different, which is why I established them up here. Okay, so AC then is 4.95I and 4.95K, and AB is negative 4.95I, and this is 4.95K. All right, so how about in the in the y direction? Well, we know that the hypotenuse of this triangle is 25. We know that this angle, in other words, between the upright and the plate, between the y-axis and the xz plane, is 73.7 degrees. So the y component is 25 times, this is the opposite, the cosine of 73.7, which it's opposite. It's not cosine, it's sine, sorry. I do that once in a while just because, I don't know. The sine of 73.7, multiply that number by 25, and you get basically 24. So the y component is 24. Now, if we go back, I'm going to plug those in. This is 24, and this is 24. Okay. If you go back to our original vector that we did, we found out that that was 24 as well, which makes sense, yes? Because they're all, unless the plate is wonky, if the plate is level, they should all be the same distance in the y direction. All right, so here's my vector AC. We know that the entire vector has a length of 25, so we can say lambda AC is equal to this number over 25 in the I direction, plus this number over 25 in the J direction, plus this number over 25 in the K direction. And similarly here, negative 4.95 over 25I plus 24 over 25J, plus, excuse me, minus 4.95 over 25K. So now I have my three vectors. I just want to simplify those a little bit. Just like here, I've simplified these to just a decimal number. I'm just going to divide these numbers. If I take 4.95 and divide by 25, I'll get just under 5. 1/5, I mean. So this number is going to be lambda AC is 0.198 I. I already did 24 over 25 plus 0.96 J plus 4.9, still that same number. Okay, so there's one of my lambdas. And guess what? The numbers associated with the lambda AB are going to be the same, but the signs will be different. So lambda AB is equal to negative 0.198 I plus 0.96 J minus 0.198 K. All right, so then I know that all I have to do is multiply each of those by the tension in each of the cables. And I've got the vectors that are going to be used for this problem. So let's set up the vector force in AD. It's going to be equal to the tension in AD, which is an unknown, times lambda AD, which is this. Negative 0.28 I plus 0.96 J plus 0K. Okay. The force in AC is going to be the tension in AC times that unit vector. This is right here. 0.198 I plus 0.96 J plus 0.198. Okay. And similarly, the force in AB is equal to the tension in AB times minus 0.198 I plus 0.96 J minus 0.198 K. All right, so if I go back to my original drawing, I see that on the plate, or whatever I want to use as my free body diagram, I have these three forces acting up, which I have defined as vectors here. And then I have the weight of the plate itself, which is acting downward. So it's negative 12 in the J direction. All right, so then I'll just set up the equations, and then you will see that you have three equations and three unknowns, and you can therefore solve. All right, summation force is X equals 0. I say negative 0.28 times TAD plus 1.198 TAC minus 0.198 TAB. In order for equilibrium, those have to equal 0. I'll leave a little workspace. I say summation forces Y have to equal 0. So I have 0.96 TAD plus 0.96 TAC plus 0.96 TAB. Only now we have the weight minus 12 pounds equals 0. And then finally, I have knocked everything off. I'm like a cat today. I've just knocked everything off the desk. So summation force is Z. I get a pass here because this is equal to 0. So I get 0.198 TAC minus 0.198 TAB equals 0. And here's my first simplifying assumption. If I solve this, I just get TAC is equal to TAB. So that's going to make my substitutions a little bit easier. In other words, I could plug that in here, and then I could likewise plug it in here. And then I would eliminate one of those variables, TAB, for example, if I plugged in TAC. And then I would have two equations in two unknowns, TAD and TAC, and then I can solve for everything. So when you do problems like this, it helps if you know where you're going, but what really helps more than anything is staying organized. Because now that you have these equations, once you plug in and do this substitute, solve these equations simultaneously, then you can just plug back in to get the other value, and then you'll know. And then your answers are just look like this: TAD equals this, TAC equals this, and those are all going to be in pounds, and TAB is equal to this. How's that? Is that helpful? Any other questions? 2.7? Let's find out. Let's find out. 2.7. Okay, so let me. What's that? Oh, that's fine. I got time. I'm not going anywhere. What's that? You got it? All right. Well, good. Excellent. Are you putting your study of trigonometry in past use in this class? So, yes, that's good. I'm glad to hear it. Now, it's like I said, this class has a Calc 1 prerequisite, but really it's trig. It's just holy cow trig. So, yeah, there you go. Good. Good deal. I'm glad to hear it. All right. So then let's go back and take a quick look at our schedule. Just to make sure everybody's on page for that. Get pulled up here. All right. And then I will share my screen. I think maybe. There we go. All right. So just to remind, we've turned in the first homework assignment. The chapter 2 homework assignment is due tonight. I'm going to extend the quiz until Friday at 11:59, just because I don't want both things to have to be done at the same time. I want you to be able to devote some time to each of those. So we'll turn that on Friday, then or by Friday, and then on Friday we have a Zoom lecture only. And then Monday, I'll be off campus, so it will just be recorded lectures on that day. All right, so everybody, if you are listening to this, please don't forget that if you have trouble or questions, send me an email or send me a text, and I will help get you squared away. The only time that doesn't really apply is on the quiz, unless it's like, I don't really know how to get into the quiz, because I will help you with things like that. But aside from that, best of luck, and call me if I can help. Call, text, email, all those things. All right. Have a wonderful day.